our customers who use Leica Bond RX and VENTANA automation systems. We will have a separate webinar to focus on these platforms in the near future. However, you can go ahead and ask your questions during this webinar, and a technical support scientist will respond to your questions directly. We may not have time to address all the questions, but we will be contacting you directly following the webinar. For rules, the audience will be automatically muted, so if you have a question, please select the chat feature button and ask your questions to the host and presenters. We apologize in advance that we may not be able to answer all your questions, but we will follow up with you offline. Again, we thank you for attending this webinar series, and you will be receiving a thank you email at the end of the webinar, including a link to our survey. We do appreciate your feedback as we continue to improve our process and products. For today's topics, we will be discussing RNAscope recommended workflow, tips for RNAscope manual and automation assays, troubleshooting staining patterns, and we'll set aside room for questions and answers. As a general introduction, for some of you this is not new, but for people who are new to RNAscope, we'll just review very quickly the RNAscope workflow. This includes permeabilization through pretreatment to access intact cells or tissues. This is followed by hybridization to target RNA through target-specific double-Z pair probes. This can be analyzed as one RNA, two RNAs, and in the case of a multiplex assay in the fluorescent system, we have up to 3 RNAs. The next step is amplification. After the ZZ pairs bind, preamplifiers bind, followed by a series of amplification steps. Binding of label probes, which are usually chromogenic or fluorescently labeled. The next step is to visualize single molecules seen as punctate dots shown here, followed by quantification. This results in a breakthrough platform that is unique in probe design, provides signal amplification and background suppression, provides single molecule detection in single cells, and a choice of any genome on any tissue. To discuss in detail the RNAscope workflow, we'll first review the products that we have available. Some of you already have purchased these products, some of you intend to purchase these products, or some of you are waiting to use these products. We have 4 basic products in our RNAscope platform. The first is 2.0 Brown, which uses the dye DAB with an enzyme reaction through HRP. This utilizes channel 1 probes, also known as C1 probes. In the Brown system, we also have probes for the VENTANA and Leica automation assays, and you'll see them denoted as VS or LS. The next product is RNAscope Red, which also applies the manual VENTANA and Leica assays. In this product, we have a substrate fast red and enzyme alkaline phosphatase. For the manual assay, the channels are also denoted as C1, and these are available for VENTANA systems and Leica system probes. In the 2-plex, this only applies for the manual assay, and 2 enzymatic reactions apply. One is HRP green, and the other is fast red and alkaline phosphatase. The two channels that you'll use for the 2-plex chromogenic are C1 and C2 probes. For the chromogenic assay in the 2-plex system, we don't have available probes or products for VS or LS. The final product is RNAscope Multiplex Fluorescent Assay, which uses label probes within the wavelength of FITZ, Psi3, and Psi5. The channels that you'll be using are 1, 2, and 3, and they are named C1, C2, and C3 probes. Also, in this platform, we do not have probes available for VENTANA and Leica systems. A quick overview of how RNAscope works. We will segment into the different products. The first product is Brown, which, as discussed, utilizes HRP enzyme and substrate DAB. The result is a brown dot following various signal amplification systems. The next is 2.0 red, which utilizes alkaline phosphatase. And as in this schematic, you see the binding of the probe, amplifier, pre-amplifiers, and a resulting red signal that's produced by reaction of alkaline phosphatase and fast red. It's important to not interchange reagents within each assay or between different assays. By default, for the 2.0 HD systems, the probes come as C1 and do not require any further dilution. In the 2-plex system, HRP enzyme utilizes the green substrate, and this reaction produces a green signal. Subsequently, alkaline phosphatase and fast red produces a red signal. By default, C1 probes in the 2-plex chromogenic assay come as 1x concentration, and C2 probes come as 50x concentration. To make the 2-plex probe mixture, you will need to dilute C2 probes into C1 probes in a 1:50 dilution. To view C2 probes only, you can use blank probe that's provided by us as a diluent, and you can still use the same dilution at 1:50. For the multiplex fluorescent assay, we have 3 options of fluorophores. One is Alexa 488, the next is ATO 550, and ATO 647. The excitation and emission wavelengths are shown here. By default, the C1 probe again in the multiplex assay comes as a ready-to-use product. C2 and C3 probes come as 50x concentration. To make the mixture of a 3-plex probe for multiplex assays, in order to view Alexa 488, ATO 550, and ATO 647 signal, you will need to mix C2 and C3 into the C1 probe that comes as a ready-to-use 1x concentration. Again, if you only want to view C2 and C3 probes, you can dilute this in the blank probe in the C1 format and dilute at 1:50. The RNAscope workflow for the chromogenic assay involves the following steps: pretreatment, hybridization, amplification, staining, and detection. The general protocol in pretreatment includes peroxidase blocking, which utilizes pretreatment 1 reagent, epitope retrieval, utilizing pretreat 2 reagent, and protease, which utilizes pretreat 3 or 4. This is followed by target hybridization, wash step, binding of preamplifier, another wash step, a series of amplification steps, washing, label probe hybridization, washes, detection, and counterstaining with hematoxylin. For chromogenic assays, you can view your image under a light microscope. It's important to note that the detection protocols will vary based on the chromogenic assay that you're using. For the fluorescent assays, the protocol is quite similar with the chromogenic. This is an example of fluorescent assay preparation for a fresh frozen sample. In fresh frozen sample, the samples are embedded in OCT, cut and stored at -80 typically. When ready to use RNAscope, you'll perform fixation, dehydration, and protease digestion. This is followed by the same sequence of processes in hybridization and amplification. The main difference is the label probe hybridization, in which the label probe has a fluorophore, either 1, 2, or 3, depending on which system you would like and how many genes you would like to visualize. This is followed by counterstaining of DAPI and imaging under a fluorescent microscope. For the fluorescent assay, the pretreatment conditions will depend on the sample type that you're using. In the manual assay, you can perform a 1-day or 2-day assay, and these are the steps involved in the 1-day assay, including sample preparation, pretreatment, and RNAscope assay. In the 2-day assay, you can prepare the samples, perform pretreatment, and utilize the optional stopping points, and proceed on day 2 with the RNAscope assay. For the automation assays, please refer to the user manual for the appropriate workflow. So we'll now discuss tips for RNAscope manual assays. For manual assays, we recommend that you revisit your protocols. For existing users, you will note that some of the protocol workflow has changed. So we encourage you to visit our website and review our protocol as we go through frequent revisions. For sample pretreatment, you can utilize our sample pretreatment guideline, and we recommend that you use controls, especially when you're starting with new samples. We also recommend that you revisit the checklist to make sure that you're using the reagents and equipment that we recommend. Here are some of the reagents and equipment that we recommend for a successful run with RNAscope. Some of them include SuperForce Plus slide, hybridization oven, and of course, using positive and negative control probes. We'll review some of these in the next couple of slides just to reiterate the importance of these reagents and equipment. The first is the hot plate, which is used for epitope retrieval. And the important thing to pay attention to is time and temperature. These are key to prevent overdigestion or underdigestion. The next is the reagent kit. Some of you are familiar with the reagent kit on the left. To the right, we have performed some improvement in the reagent packaging outlook and information on the packaging, which includes storage conditions and expiration dates, as well as lot numbers. In the reagent kit, just remember to warm probes at 4 degrees before you begin in case there's precipitation, and this also applies to the 50x wash buffer. It's important to notice that nothing has changed in these reagents, only the packaging has changed. The hybridization oven is important to maintain both temperature and humidity. If you're experiencing issues with your assay, we suggest that you consider using hybridization, the HYBEZ hybridization oven. We have found that consistent results are attained when you use this system. If you have questions about the HYBEZ hybridization oven, or if you require to attain one, please contact us in technical support, and we'll direct you to the right channels. Accessories for washing are very typical with the item on the left, which is the TissueTech washing tray. This works well with most users. However, high-throughput users may find it useful to use the EasyBatch slide processing container. This allows for placing slides, loading slides without removing through hybridization and washing steps. If you have questions about the EasyBatch slide processing equipment, please let us know and we will direct you to the right channels to get it. We will now review some of the guidelines for the manual assay. This information is available in our troubleshooting guide that's now available in our website when you choose the support tab. Here are some things that we think could be useful for you, including making sure that the residual reagent is removed when you're washing and after washing and when you're adding the reagents. Do not let the slides dry out, and we encourage you not to alter the protocol in any way. We have optimized the protocol for your use for all your samples and assays. We recommend that you use fresh reagents, and some of these reagents that are used routinely include ethanol xylene and neutral buffered formalin. We will now review pointers for each assay. For the 2-plex 2.0 red assay, the most important element is to use EcoMount or Patex as mounting medium. We have tested xylene-based mediums that some of you may be familiar with and found that this causes diffusion in the signal. Another element that causes diffusion in the signal is the use of alcohol. To avoid this from occurring, please use EcoMount or Patex consistently for your assay. In the 2-plex chromogenic assay, the most important note for you is to make sure that your reagents are mixed accordingly. Here is a table of the reagents that you will need to mix for the 2-plex assay. Once you mix, you will simply add the reagents as recommended in the protocol. As a reminder, for the 2-plex chromogenic assay, C1 probes are ready to use and C2 probes are 50x concentrated. We've already visited how to make two-plex probes using C1 and C2 probes. And also, if you just want to view one of the probes, in the event that you just want to see a single-plex staining, you can dilute the probes using the blank probe. In the multiplex assay, we have the following color modules. This will allow you to visualize green or red and far red signal using different combinations. It is important to note that these color combinations are not to be mixed, and you can choose the one that's useful for your applications. For automated assays, we are going to review some of the tips that we found useful. The first tip is instrument maintenance, software settings, troubleshooting reagents, and performing sample pretreatment. For automated assays, visit our troubleshooting guide for additional information. For the VENTANA Discovery XT or Ultra assays, these are the following information that we found useful. Performing instrument maintenance, performing decontamination protocols frequently. It is recommended to perform every 3 months, using appropriate buffers, and remembering to purge reagents before a run. Optimizing software settings by unchecking the slide cleaning option. This applies for the Ultra only. And this is important as this is a cleaning step that is a part of the VENTANA equipment maintenance, but not applicable for RNAscope. When checked, this slide could dry out and can affect the results of your assay. We also recommend that you use appropriate hybridization temperature applicable to XT and Ultra systems. For the Lycabond RX system, we recommend that you do not shake the contents in the containers, as this will form bubbles. We also recommend that you warm the following reagents: LS AMP1, AMP3, and the wash buffer. Also take note of the reagents that you need for each of the LS assay systems, and also do not alter the staining protocol in any way. We will now discuss how to qualify your samples using either manual or automated assays. The first step is to understand the image analysis process. This is a scoring guide criteria that has a scoring of 0 to 4, with 4 being the highest score. On the right is the scoring criteria, which is dependent on dots per cell. And here is an example of what we consider a score of 3. To qualify your samples, we recommend that you first start with control slides. Typically, you will get HeLa or 323 cells. Use negative and positive control probes and perform a technique check. When this check passes based on your scoring criteria, go ahead and perform a sample control qualification using negative controls and positive controls. If this passes the quality control check, you should continue to run your target probes. If this fails, you should verify the technique again, check that your RNA quality is intact, and perform assay optimization. As a recommendation, we always require that you start with standard conditions to know the status of your sample. This is just an outlook of how to perform optimization, performing technique check, sample and RNA quality check. In the event that the technique check fails, you can repeat and revalidate the technique. And if the sample quality check fails, you can optimize and retest. Once the sample check has passed, you should proceed with your target markers. If the sample check fails, perform optimization of your assay. We will now review optimization of your assay. Many of you may wonder why we recommend optimization. The following are some of the points to review before performing your assay and determining when to optimize. Some of the conditions that will require optimization are when samples are underfixed. The following conditions we have found to be underfixed for RNAscope. As an example, as you know here, the temperature of 4 degrees may work well for IHC, but for RNAscope, this is considered underfixed. Similarly, overfixed samples are when the length of time in fixative is longer than what we recommend. Our standard recommendation is 10% NBF for 24 hours. We have found that sometimes 48 hours is long and presents overfixed samples. In some cases, you're using sample types that are unique and are more susceptible to pretreatment. You should perform pretreatment optimization in these samples to determine the best conditions for your sample and your assay. Other samples are inherently more difficult to penetrate, such as liver and muscle. These samples may require extended pretreatment. Additionally, there are some samples that tend to be susceptible to pretreatment, even when fixed according to what we recommend. These samples include spleen, tonsil, and lymph node. In this case, you will require to optimize your assay. The factors that are affecting assay performance we've already reviewed, but some of the highlights are sometimes you may not see signal, or you may experience a weak signal because your RNA is degraded. In this case, you would need to acquire new samples. If you're finding that the hybridization system you're using is giving you inconsistent results, we recommend that you use the HYBEZ hybridization system. This is the only oven that we have noted gives consistent results. Sometimes the samples dry because the hydrophobic barrier is not intact. We have tested and found that the image hydrophobic barrier pen remains intact through the assay. If you have special tissues, you may want to start with standard conditions and then optimize your assay. To optimize your assay, perform the following treatment conditions in the following steps. For the manual assay, you will be faced with two types of samples, underfixed or overfixed. Here is the optimization using pretreatment to epitope retrieval step, also known as boiling. If your sample is underfixed, you should decrease pretreatment 2 times. And if it's overfixed, you should increase pretreatment 2 times. This is a guideline of the time that you can use to optimize your pretreatment. You may need several pretreatment conditions before you can find the ideal condition. If you need guidelines, you can contact us in technical support, and we can provide you with some recommendations and suggestions. Subsequently, with pretreatment 3 and 4, which is a protease step, if samples are underfixed, you want to reduce this time in the protease treatment. And if overfixed, you want to increase the time. And again, these are guidelines, and you may want to perform this with different conditions to find the ideal conditions for you. It's important to note that for cultured cells, the protease is typically diluted as a starting point of 1 to 15 in PBS. To optimize your automated assays, here are recommendations for LicaBond RX. For overfixed samples, you should increase ER2 time in increments of 5 minutes and protease time in increments of 10 minutes. For VENTANA, increase pretreatment 2 and 3 and or cell conditioning time. For underfixed or overdigested samples, reduce temperature to 88 degrees. This has been shown to improve morphology and reduce background. This is slightly different from what we do with overfixed samples, but we have tried this recommendation and find this is the best condition for you. For VENTANA, for underfixed samples, perform a decreased pretreatment of pretreat 2 and 3 and or cell conditioning time. Here is an example of a successful RNAscope result. It shows the clean DAP-B signal, robust PPIV staining, and a specific target probe staining. This is what you'll be looking for all your results when you get an ideal condition for your assay. You can visit the troubleshooting guide for additional information on how to acquire results that have clean DAP-B great positive PPIB, and great target probe signal. For the multiplex assay, this is an example of a 3-plex positive control probe, which contains POLAR2A, PPIB, and UBC. And as you can see, the specific staining pattern of each of these targets using the AMP4 Alt-A reagent. It's important to note that you can use these different reagents if you would like to visualize your signal in different wavelengths. However, these 3 reagents that we have available in our kit are not to be mixed. We will now troubleshoot staining patterns in the CHROMOGENIC manual. For a no staining signal, the common issues are suboptimal fixation, inappropriate hybridization temperature that's not optimal, reagents that are used in the wrong sequence, and perhaps your gene of interest is not expressed. To the right are the recommendations that we have for these issues, such as using the HYBEZ oven and making sure the temperature is according to what we recommend for hybridization. For over-fixation and under-fixation, we recommend that you always prepare your samples according to ACD recommendations and optimize your pretreatment conditions. If your gene of interest is not expressed, you should check the positive control to determine that your technique is accurate. Sometimes it's likely that your gene of interest is not expressed when you're comparing with other technologies such as PCR. You should call ACD technical support when you're faced with this problem, and we can guide you with appropriate suggestions. This is an example of troubleshooting sample digestion. This is what you expect for optimal digestion. PPIB staining is robust and the DAP-B signal is clean. In the same xenograft tissue, we performed an under-digestion protocol. We simulated this protocol by pretreatment at 8 minutes, boiling, and 15 minutes protease. As you can see, the morphology looks as though the sample has not been penetrated, and the PPIB signal is weak compared to the optimal pretreatment. The solution for this is to increase your pretreatment protocol. In the over-digestion protocol, we simulated and increased pretreatment 2 to 15 minutes and pretreatment 3 30 minutes. As you can see, the sample looks over-digested, where the nuclei is exposed and the counterstaining is not as visible. Although PPIB staining is still robust, the DAP-B background will guide you to determining if this is an optimal assay. To address this, you should decrease pretreatment and perform the assay with the optimal conditions. Here's an example of a kidney FFPE tissue that shows high background. In this case, standard conditions were used. However, you still see high background. This suggests that this sample may have been under-fixed and over-digested. To address this, we reduced pretreatment 2 to 7 minutes and kept pretreatment 3 unchanged. The result here is that the background is now clean. This is an example of a staining pattern using the Leica system LS Brown in the Leica Bond RX. In the Leica system, you will notice that a nuclear hazy background may occur when the sample is under-digested. To address this in the Leica system, you increase the ER2 in 5-minute increments. In this case, we used 20 minutes and kept the protease consistent. The result is a clean background by following the 5-minute increment protocol. Another troubleshooting pattern is assay workflow related issues. This is an example of a sample that dried. This resulted in nonspecific binding of amplifiers and caused amplification of signals that may look like real RNAscope signal. However, this is superficial and not real signal. Subsequently, there is an inherent haze in the sample. This is usually caused by samples drying between amplification steps. And to address this is to follow the protocol as recommended. Some of the tips are listed here, which includes covering tissues with appropriate volume of reagents, making sure that the slides are processed one at a time when you're using the manual assay, using the hybridization oven at the appropriate temperature, and making sure that your hydrophobic barrier is intact. Some other reasons why you may see this staining pattern, particularly the hazy background, is incomplete paraffin removal and suboptimal tissue preparation. To make sure that your paraffin is completely removed, make sure you're using unused fresh xylene and ethanol. And also make sure that you're moving your slides up and down as recommended in the protocol to make sure that the paraffin is removed. You should also prepare samples as recommended in our manuals. Sample preparation issues always result in samples falling off. This is a xenograft tissue in which the sample has fallen off. The reasons why samples fall off tends to be detached slides because wrong slides were used. We recommend using Superforce Plus slides. If you've used the slides and you're still seeing this issue, it may be because your tissue is not prepared accordingly. Some of the measures to take is to prepare tissues according to recommended procedures. However, you can also try baking slides for a longer time. We have tried 1 hour and sometimes have gone up to overnight. You can also try mitigating this issue by reducing the boiling time. As you can see here, a standard baking protocol results in tissues falling off, while if samples baking is increased by 1 hour, you notice that the samples remain intact. Here's an example of troubleshooting of suboptimal fixation conditions. To the left, the sample was fixed according to our recommended protocols, and to the right, the sample is overfixed at 3 weeks. The signal is weaker here and may alarm you because it's not as we expect for RNAscope when running optimally. In this case, you will need to increase the pretreatment conditions in order to have an optimal signal present. Other issues that we've seen with RNAscope is that you may face in your laboratories is when you receive tissue with unknown preparation method. These typically come from sample providers or vendors where the fixation and preparation conditions is not highlighted. When facing this issue, our suggested action is to, if you can, share the appropriate tissue pretreatment and preparation protocols with your sample provider. If you cannot do this and this is out of your control, we recommend that you start with standard conditions, and if this is not optimal, optimize your assay. Another issue we face is diffuse red signal. This is due to the stability of the fast red chromogen. In the 2.0 red and the 2-plex chromogenic assays, this is because sample is not completely dried. Another reason is performing dehydration using alcohol. A third reason is using too much mounting medium that retains an inherent wet-like condition in the sample. To address this, dry samples as recommended. It may require that you prolong your drying if you see this issue consistently. We recommend and insist that you do not dehydrate samples using alcohol. Only dry samples at 60 degrees for 50 minutes to start with. If additional drying is required, please call. If you think additional drying is required, call us in technical support. We'll be able to suggest some timelines for you. We also recommend that you use EcoMount sparingly and not overload the sample with EcoMount, as this will help mitigate this issue. Here is an example of troubleshooting under fixation. In this case, The user first flash froze the cells and then performs FFPE sample preparation, a series of dehydration steps embedded in paraffin and cut. This resulted in a weak tissue and loss of RNA, as shown here. However, if samples are prepared as we recommend, 10% MBF at room temperature for 16 to 32 hours, you see that this issue has been mitigated. For sample preparation procedures, you will find this information in our user manuals. Here's an example of troubleshooting green signal fading. This is primarily inherent in the 2-plex assay. As shown here, the signal was originally present, but with time the signal has faded, and sometimes you see this issue immediately. The causes that we have identified for this issue is hematoxylin or any associated low pH in the reagents, as well as the bluing with ammonia water. We have highlighted the steps of making ammonia water, but in some cases the ammonia water pH is not appropriate. This causes an instability in the green signal. Also, if you incubate with a 2-plex assay a prolonged hematoxylin protocol, we have noticed that the green signal will fade. We recommend that you use hematoxylin as recommended in this assay, and this will help mitigate this issue. If you're consistently experiencing green signal fading with ammonia water, we recommend that you use tap water instead of ammonia water. Now that we have reviewed the staining patterns that you may experience and require troubleshooting, here is a pretreatment guide for manual assays. And here you can see in Table 1 guidelines of how to perform pretreatment as a starting point. There are mild, standard, and extended conditions. And to the right here is a table of different samples that we've tested and recommended pretreatment conditions. You will find this information in our user manuals. This is specifically highlighted for formalin-fixed paraffin-embedded samples. For other sample types, we have technical notes in our website to guide you on how to work with these samples. Here is an example of pretreatment guide for VENTANA Discovery Alter. And as you can see, we have performed different protocols for different samples to give you some guidelines for the VENTANA system, and also giving you some guidelines for how to initiate pretreatment optimization protocol. For multiplex assay, the main issues that you may face is sample digestion. Here we see that the temperature affects sample digestion. For fresh frozen samples, as shown here in mouse kidney and mouse brain, we recommend room temperature as the optimal digestion protocol. When you use the hybridization oven or any other 40-degree temperature with any equipment, you will find that the sample becomes over-digested. This may lead to weak signal and perhaps no signal with your particular target. Another sample digestion issue that you will face with fresh frozen tissue, as shown here with mouse brain, is the thickness of the sample. As you can see, although the signal comes through with 10, 15, and 20 micron, you see the signal much weaker in 10 micron. Therefore, if you have a weakly staining target, you may lose the signal if you use a thinner section. We therefore recommend that you optimize your protocol to determine the best thickness for your assay. 15 micron seems to be most popularly used, but our assay and our recommendations are to use within a range and determine the protocol that works for you. Here is an example of a series of issues we see with autofluorescence. Here is a mouse FFPE kidney, FFPE intestine, colon, and brain. It's important to note signal that is not RNAscope signal. As an example, this green signal is not considered RNAscope signal. This is merely autofluorescence. To address this, the best way we have handled this is to use a background correction software. So in summary, for multiplex assay, two issues tend to prevail: microscopy and the sample. For microscopy, usually make sure that you have the right filter settings. Make sure your exposure is according to what your microscope settings indicate. And also, before you set up your exposure, make sure that you're seeing the signal with your naked eye first. If possible, use the image enhancing software to address the autofluorescence that you observe. We typically use new ones for this purpose. If your signal is weak or you see no signal at all, it may be that your sample has compromised RNA quality. You may need to get new samples and perform a quality control check for your RNA quality. Also, if your sample preparation is producing high autofluorescence, you may want to revisit the recommended protocols for sample preparation. You can also consider performing pretreatment optimization for your samples when you see no or weak signal. We recommend that you always perform positive and negative controls to assess RNA quality, and also always trust your eyes first when you check for the signal before you use the microscope, so you can capture what you're seeing. And these are just summaries of a summary of what we have discussed. We encourage you to use the sample preparation protocol part 1 for your assays when you're using multiplex fluorescent assay. Another recommendation is to use 3-plex positive control and negative control to assess RNA quality. And as indicated, always evaluate the results by your naked eye first. We're now going to visit frequently asked questions. And these are the most frequently asked questions that we have seen. One is the compatibility of RNAscope with different tissues. Some of you may have started with formalin-fixed, paraffin-embedded tissues. However, we have protocols and technical notes across different platforms, and you can find this in our website. We have fresh frozen, fixed frozen, cultured cells that you can use with our chromogenic and our fluorescent assays. You can utilize the user manual selection guide in our website. Another question that comes up is the key differences between ISH and IHC. RNAscope ISH is basically, the basic differences are the epitope retrieval step. In RNAscope, after boiling, do not allow the samples to cool. Go directly to pretreatment 3 by placing your samples in water and proceeding as recommended. This applies for manual assays. As a summary, we have discussed the recommended workflow for manual and automated assays. We have discussed tips for RNAscope manual automated assays, which includes instrument maintenance, software optimizing your software settings, and importantly, optimizing all your assays, whether manual or automated. We have also reviewed troubleshooting staining patterns. We have looked at high background staining patterns, conditions where you see no signal, and situations where you're observing sample detachment. We've discussed how to optimize your assay using pretreatment 2 and 3 for manual assays, adjusting ER2 or temperature with the Leica systems, and performing offline pretreatment optimizations. And as a note, you can also perform online pretreatment optimization when you're using the fully automated VENTANA protocol. We've discussed how to adjust cell conditioning and pretreatment 2 and 3. And as a reminder, we will be available to answer any questions on the automated systems and plan to address additional questions in a separate webinar for the automated assays. We encourage you to visit our support webpage by visiting the support tab. Here you'll find support overview, including training webinars such as this one, downloading your manuals using the user manual selection guide. For those who are new to RNAscope or those who want to revisit how to get reacquainted with RNAscope, visiting the Getting Started page. We have a troubleshooting guide now available. We also have additional frequently asked questions, online training videos, and product literature, especially visiting our publication list to see all our applications and application reviews. We encourage you to contact support. Those of you who have been with us for a while know how to reach us. This is our email, support@acdbio.com. You can reach us by phone between 8 a.m. and 6 p.m. Pacific Standard Time. We also have several support resources as highlighted here. Just to reiterate, manuals, getting started, frequently asked questions, videos, and product literature. At this time, we will entertain any questions that you have, and please remember to complete the webinar survey at the end of this webinar, as we do value your feedback. Thank you for your attention. We have a question asking whether the PDF of this presentation will be available on the website. We'll ask for your patience as we upload this information on the website, so we will check back with you and give you a reasonable timeline of when this information will be available. And thanks for asking that question. As far as questions about the target probe region, for the exact sequence, we do have that on our website, and you can find that information. The exact sequence is proprietary. However, you can find the general information on our website when you are searching for the probe. Another question is whether it's possible to dilute probes with water to reduce the concentration of the probes and therefore the background signal. The answer to this is no, we do not recommend or suggest that you change the probe concentration in any way. The only time you're encouraged to dilute the probes is when you're using multiplexing, and we have highlighted that you can use the blank probe that is presented with the various formulation compositions for optimal hybridization. The probe concentrations that you have as ready to use are optimized, and you do not need to dilute them any further. To reduce the background signal, you need to perform pretreatment optimization rather than changing the composition of the reagents. Another question is, I'm working with mouse kidney and liver FFPE samples. Some of the samples are fixed for less than 12 hours. I understand that the signals in these underfixed samples may be faint. Are there any modifications that I should make to the standard protocol? So this is a sample that's underfixed, and what we recommend is that you start with standard conditions as we went through and highlighted the optimization protocol. And based on that, you can perform conditions accordingly. It's highly likely that with this sample, you will need to reduce the pretreatment protocol from the standard condition. However, the purpose of performing the standard pretreatment condition is to determine the status of your assay and your sample. Another question is, I have ready access to tap water, reverse osmosis, or molecule equivalent water, but not distilled water. Could one of my waters be used in place of distilled water? We typically use molecule water, so this is sufficient for RNAscope. Usually only washes performed after the hematoxin step can be used with tap water, or in the case of the multiplex when we're seeing the green signal fading. Do not use any other type of water, for example tap water, when washing through the RNAscope assays. This can affect the results of your assay. Another question that's come in is, we have observed binding of the nucleus in the FFPE liver tissue. Would that be overdigested? And the answer to that is, it is likely overdigested. And for mitigating this issue, just follow our pretreatment optimization protocol. It is likely that you will need to reduce your pretreatment. Also, double check to understand what the fixation conditions were, and if you do know them, then you can compare with what we recommend, and if it's underdigested, and in what manner, whether it's temperature or the fixative used. In any event, for this particular issue, it appears that you will need to reduce pretreatment. If you have any further questions regarding this, you can contact us in technical support, and we can provide you with some guidelines for how to address this issue. If you have RNAscopes that are from very old samples, for instance 5 years, these are considered archival samples. We have seen that RNAscope can work with archival samples. However, because at this time we may not know the fixation conditions of the sample, we recommend again to start with standard pretreatment protocols, assess the quality of your RNA, and proceed accordingly. If the sample is consistently failing the pretreatment optimization protocol, you can contact us in technical support, and we can provide you with guidelines as to whether the sample still has intact RNA or whether you need to perform further optimizations. For any specific questions that you're asking about the VENTANA system and Leica systems, we will reach you directly. I see a couple of questions that require more specific specialist attention, so we'll reach you directly and address your questions for you. And thank you for your question. So another point to point out is quite a few questions regarding the availability of the webinar. It may not be available today, but we will make an attempt to put it up as quickly as possible, as we understand you want to re-review the webinar contents. Also, please remember to contact us in technical support if some of your questions are not addressed and you want immediate assistance that may not be available for you in the webinar, since we're not certain that we will have the webinar on the website today. So just contact us in technical support if you have an immediate question. At this time, I would like to thank you for attending our webinar. Remember that if we did not answer your questions directly, especially if you have specific questions for automation systems, we will reach out to you directly. We encourage you to visit our support page and contact us in technical support. We are always happy to work with you and entertain all your questions so that you're successful with RNAscope assay. Have a great day, and thanks for attending. Goodbye.